All right, okay, yes. So as Dave kindly introduced that, we're going to talk about choosing the best chemical system and then finish off with handling iron 3+. And this has been somewhat touched on, I think, throughout the workshop. Uh, People asking, as Mark said at the start of his talk today, is there a best chemical system for X rock? And the best chemical system is totally dependent on what you're trying to model. What rock type are you considering? Which PT conditions are you interested in? And even what's the specific problem that you're trying to solve that's linked to these? Do you need the added complexity of more elements in your model? And so the, I suppose, disclaimer here is that this short talk is not going to give you the correct answer for your rock or any rock, because there isn't a one-size-fits-all solution. But I hope that it will show you the factors you should consider when you're making a choice about which chemical system you should use. Some example diagrams produced in different chemical systems to show you the effect of choosing a different chemical system. And then finally, ways to consider iron 3+ as a component linked on to getting more complex in our chemical system. And so I just quickly put up this table from Pierre's paper here that he showed in his first talk that shows the increasing number of elements that are included in these thermodynamic data sets through time. So we slowly add more and more as we go to the bottom of the table here. And the question is, again, is more necessarily better? Should you be including every component that's possible to include? And are more complicated systems going to reproduce nature better than your simpler ones? So to answer this this first question, what factors should you consider? I've pulled up this table here, and this is it shows the weight % oxides along the top and the average bulk metapolite that I was using in my calculations yesterday and will be using again today. And so the point here is that we've been able to explain the majority of phase relations in metapolitic rocks using KF MASH since Thomson. And, I've highlighted these, one second, oops, there we go. I've highlighted these in red here. And so you can see that the majority of these elements, they represent the more major elements in metapolites. So, lots of silicon, aluminium, iron, magnesium, potassium, and then hydrogen included as well. But there are also these more minor elements. So there's the major elements. There's the elements that make up less than 2 or so weight % of the rock. You have titanium, ferric iron, manganese, calcium, and sodium. And there are plenty of examples where these play an important role in the stability of minerals and their modal abundance and the assemblages that occur in rock. So titanium is important not just for our minor oxide phases, ilmenite and rutile, but also biotite. Fe2O3, well, that's a component of muscovite, biotite, hematite if you've got oxidized rocks. Some examples there of papers that show that. Manganese, even though it's perhaps the smallest of all of these components in terms of its weight %, really important for garnet stability, amongst other things. Calcium goes into your plagioclase and your garnet, restabilizing garnet, and then sodium in terms of the going into albitic plagioclase, stabilizing paragonite and being a small component of muscovite. So yes, KF MASH explains the board changes, but these minor elements are also quite important. And so firstly, when you're deciding what chemical system to use, look at your bulk composition and have a look at what elements are there. The second thing that you probably need to consider is what elements are available in the data sets and solution models. You may have all of these elements present in your whole rock that you've made, but there are also limitations to what we can do in terms of the data sets and the solution models. And so what I've done here is just simply said that the majority of solution models are going to have a silicon, aluminium, and iron, and magnesium, and a potassium end member where appropriate. But different data sets and solution models have different end members for, or more or different end members for the, for different, I suppose, I've totally lost train of thought here, for different minerals that I've listed along the left-hand side. And so what I've done here is I've put my 3 databases in, HP1, HP2, and DS62 with their different solution models. And you can see that HP1 has quite a bit wide variability. You've got titanium and ferric iron and manganese added to biotite. manganese added ideally to lots of N members, and this box is wrong. This should be over here on rutile. I forgot to change that, apologies. And you've got sodium and calcium added to this system where they're important for garnet, plagioclase, and muscovite. If we look at HP2, which is a slightly newer set of models, you see more ferric iron N members here for garnet and ilmenite that may or may not be important. And then in dataset 62, we add lots of ferric iron N members, especially for muscovite, chlorite, staurolite, and cordierite. So you've got to make a decision about which of these datasets you use and which one provides the N members that are most appropriate or important for your modeling. They're the kind of two main factors that I consider. Okay, so the second point I want to make is, well, what does it look like if you decide to model in different systems? So this is the same diagram that I showed yesterday for dataset 55 HP1, and just a reminder of the solution models, and this is the full system diagram here. And what I'll show you is what happens if you take the same composition and you model it in different chemical systems. So the top diagram here, this is if you go really simple and model in KF MASH. You can see there's quite a wide, large staurolite field here and our cordierite at lower pressures. We can add manganese into that since we know manganese is such an important component for garnet, and it totally changes the stability field of garnet. It goes to much lower temperatures and lower pressures. The next logical thing to add would be our sodium and our potassium to stabilize other things. Here you'll see that the staurolite stability field changes. We go from having a staurolite stability field up to 11 plus kilobars to one that's cut off at 7-8 kilobars with the introduction of groschula as a component in garnet and plagioclase across the entire diagram. This also introduces epidote and paragonite at lower temperatures and high pressures. So more complexity added to our diagram, perhaps explaining the phase relations better. The next addition would be titanium. And this diagram here, you'll see, adds these gray lines as I've shown them. These are the changes between your ilmenite and rutile, your iron or titanium oxide phases. And the other things that change, and this is similar to what Dave Waters pointed out in his talk on Wednesday, the garnet field shifts. And that's because you introduce ilmenite, that's an iron titanium bearing phase. So it pulls out a lot of the iron or some of the iron in the bulk composition, and in turn you end up with a stability change for the garnet field. And then finally, you could add oxygen to the system and have ferric iron present. This is the diagram I showed yesterday, the full system diagram. And you'll see here that there are some changes compared to what we observed in the left-hand diagram here, the diagram D. But one of the big changes is that magnetite is now stable across the entire field. And I'll talk a little bit more about this ferric iron later on and whether that's an appropriate assumption to add the complexity. So the big takeaway from this is that you seem to you get more fields, more of these small fields in which you could place your pressure temperature estimate. The question is whether or not they're really that useful to you, and how dependable are these small fields between ilmenite and rutile and magnetite and these iron titanium oxide phases. And so what I did here was I just went into pixel maps in Domino and I plotted up the volume percent biotite for each of these different chemical systems. And so what I think comes out here is that the broad changes in biotite mode, and you can take this to represent the mode of the major phases that form within metapolitic rocks. They're the same from diagram to diagram. Okay, there's maybe 35% biotite in this pink field here, and it's down at 25%, but the changes occur at the same places that are described by the KF MASH relations. So the biotite stability is enhanced in these bottom three diagrams to lower temperatures, but there's a big jump in biotite modal percent here at the chlorite out reaction as we produce staurolite or cordierite, depending on the pressures you're at. So there's a limit to how much adding more N members actually, I suppose, helps your calculation. And KF MASH does a really good job at explaining the major reactions that occur, but some of the subtleties that occur in these more complicated systems are sometimes useful. Okay, so this bottom right diagram is where I've added iron 3+, and we had a lot of people when we sent out the original questionnaire asking what topics you'd like to cover, asking about, we'd like to know how to handle iron 3+, and that's the kind of second or the third part of this talk. And I briefly kind of mentioned this yesterday, in that I was talking about minerals, but here I'll talk about it from a whole rock point of view. If you've got your average metapolite, this is the same as before, apart from you'll see I've combined my iron into total iron as FeO here, because this is quite common. We don't know how much iron 3+ is on rocks, especially if you've not been able to go and measure it. And so the same question as I asked yesterday, what's the proportion of iron 3+ in this, iron 2 versus iron 3? And in my mind, there are two ways that you can deal with this or get at this number. You can go and measure iron 3+ in the bulk rock or in your minerals and then combine it with modes to get a bulk rock. Or you can estimate iron 3+, either in the bulk rock based on comparison with other rocks or in the minerals and combine it with modes. And then you take these two and you might compare that with what you get when you're doing your phase equilibrium modeling. So I can go through these slides quite quickly, but the first option A is that you measure iron 3+, and you either measure your total iron with XRF or ICP-OS or something, and then you conduct a titration or even Moss-Bauer to get the proportion of that is iron 3+ to iron 2+. The pros of this is that it's pretty commonplace in commercial labs if you want to get a titration done alongside your XRF or ICP-OES analysis. The con is that it's a bulk analysis, so it's hard to consider a reactive bulk composition. It includes any late alteration or retrograde minerals that might have formed under a different oxidation state. And often we consider this as a maximum value because there's possibilities for oxidation during sample preparation and crushing and incomplete dissolution during the actual titration. So that's one option. The other option is that you go and measure it in your minerals, and you can use wet chemical methods or Moss-Bauer or Zanes. And this is great because you get values for your individual minerals, which means you can adjust your reactive bulk composition if you're building it out of modes times comps. The cons are that this isn't really routine. It's pretty time consuming. You've got to separate minerals if you want to do wet chemistry or Moss-Bauer. There's relatively few Moss-Bauer instruments, and it's hard to get time at a synchrotron if you're going to do Zane's work. And the uncertainty can be quite large. Either you're doing wet chemical and Moss-Bauer spectroscopy, where you take a bunch of your, you take your separates and you combine them all together and you get an average value, or you do Zane's where you're in situ, but the precision of the result isn't quite as good perhaps, and you get a large uncertainty on each measurement, even though you're measuring in situ. So these two techniques are great, but perhaps measuring in minerals isn't something we're all going to be able to do. And so the other option is that you estimate iron 3+, and you can either do this in your whole rock by comparing with other analyses in the literature. And I showed this diagram yesterday of, there's lots of values in the literature for different that have wet chemistry done or titrations done to look at the iron 2, iron 3+. This is a little problematic because you really have to understand the minerals that are in your rock. Firstly, you want to understand what the iron oxide phase is. That's perhaps a clue as to what the oxidation state in your rock is. If you've got hematite, it's more oxidized compared to some of the other, compared to magnetite or ilmenite or no iron oxide in the rock. And then you have to be very careful to consider that in relation to the other silicate minerals that exist in the rock. So are there other significant sinks of iron 3+? You may well have hematite in a rock, but if none of the other minerals take in any iron 3+, then that doesn't necessarily mean your rock is really oxidized, because the hematite is the only place where the iron 3+ could go. Whereas if you have hematite with amphiboles that can take in quite a bit of iron 3+, or biotite, etc., perhaps that's an indication that you've got quite an oxidized rock. And then the second option to estimate is that you estimate it in your minerals, and you can do this based on charge balancing or stoichiometric constraints. I've used the categories off the John Schumacher's 1991 paper here. I think this is really clean. He talks about it being easy for these minerals that have a fixed amount or number of cations and anions, garnets, pyroxenes, etc. You can also do it in amphiboles because these are category 2 and they've got one partially filled site, which allows some stoichiometric constraints to be given, that allows you to pull out perhaps a estimated iron 3+. And then there's category 3 where you have these minerals with more than one partially filled site that I talked about yesterday, and you can really only estimate it in those based on comparison with analyses in the literature. So the same as what you'd be doing on the left-hand side. And the pros of this, well, this is really easy to apply, and if you're doing EPMA work, then you already have the values anyway. And the cons, well, accuracy depends on the mineral analysis, and this is both on the EPMA analysis that you originally collect, or the analysis of the authors that you're making your estimate based on. So there are issues with that. So that's the two ways you can get at iron 3+. You can either estimate or you can measure. But what does this mean for what do you want to do when you're doing your phase diagram modeling? That's why we're here for this workshop. We're looking at doing phase equilibrium modeling. And so you can, what I'd recommend is you can plot a TXFE3+ diagram. And if you want more information on this approach, and I should have put the reference in here, but go and read Johan Diener and Roger Powell's 2010 paper. They deal with this in some detail. And what I would say is when you're making a TXFE3+ diagram, you're not trying to get the XFE3+ in your rock. Our models aren't perhaps that developed yet. Instead, you're just trying to make sure that the estimate you make is consistent with the models that you're using. And so on the right-hand side here, I put this for 5 kilobars and temperature from 400 to 700 degrees C, XFE3+ diagram from 0 to 0.5. And you'll see that this is really nice. You can look at the oxide phases in this average metapolite, and it's ilmenite at lower XFE3+ values. And as we increase, we add magnetite to the assemblage, followed by hematite, and then ilmenite leaves the assemblage at these broad amphibolite facies conditions. And so if you know the oxide phase in your rock and you understand the other silicate phases, you can perhaps start to use this to make sure the estimate you make fits with what you're using in the models. There's one caveat with this, and that it's kind of related to what I talked about yesterday. Different solution models incorporate varying amounts of iron 3+. And so this diagram on the right-hand side, it shows you the magnetite inlines plotted for the various data sets that I used, HP1, HP2, HPT, and dataset 6.2. So this is why it's really important that you're just getting the XFE3+ that fits with your models, because in HP1, as soon as you introduce any iron 3+, you pretty much always stabilize magnetite across a wide range of temperatures. Whereas the other data sets, HP2 and HPT, are quite similar here. You need about 0.05 XFE3+ in order to introduce magnetite, and then even more in dataset 6.2. And this is because there's a different number of N members of iron 3+ in the minerals in each of these data sets. And even, between HP2 and HPT, the difference here is that the Tachmanova model takes in more iron 3+ compared to the White 2007 model. And I showed that in some calculations yesterday. So I don't have a conclusion slide because this was meant to be a really short talk, but be very careful when you're thinking about your chemical system and your data sets, and plot TXFE3+ diagrams to try and get at the XFE3+ of your that you should be using in your models. And I would, take this diagram, plot it in multiple data sets, and then overlay, if you've got an estimate for or a measurement in your whole rock or an estimate in your minerals times modes, overlay these on this and have a combine all three to work out what should I be using. And I think that's everything. So I can leave it there, and if there's any questions, take those.
Thank you, Jacob. Yes, we have a few questions for you. And the first one, so we stay first on the ferric iron. So if we were interested to model with iron and titanium, so for example, ilmenite, magnetite, rutile, which database, in your opinion, does a better job at the moment?
If you want to do ilmenite, magnetite, rutile, then you've got magnetite, which means you need to be considering iron 3+. So it's iron 3+ and titanium. I would say go and look at the compositions of ilmenite that are being predicted. From what my experience testing these four, there are wide differences in which ilmenite model you use and what the composition is that it predicts. The HP1 uses quite a simple ternary ilmenite model that has just, I'm sorry if I'm wrong here, I can be corrected by Doug, iron, titanium, and I think manganese, or a small amount of manganese. There's no iron 3+ in that model. And from the ilmenite compositions I've measured and looked at from my probe data and in the literature, there's never a ton of iron 3+ in the majority of ilmenites that are measured. I compared that with HP2 and HPT and others, and sometimes there's more iron 3+ than I've seen in the natural observations. Yes, but then the issue there is that you stabilize magnetite over the entire field in HP1, because the only minerals that can take an iron 3+ are biotite, epidote, and magnetite. And so that diagram I showed earlier on might not work for most rocks. It's this problem here that the magnetite inline is really, really low in XFE3+ space. So there's pros and cons of each. Dataset 6.2, yes, maybe the magnetite inline's higher, but you're then using lots of silicates with end members that aren't that well experimentally constrained. And so I'd argue that's perhaps not a good thing. But yeah, the answer is I don't have there isn't a better job or one that does a better job.
Thanks, Jacob. I have a comment on this figure that the idea to make a temperature X FF3+ diagram to see the oxide stability is a very good idea. So it's super helpful. And maybe just a clarification on that diagram. With the most recent data set, DS62, where is all the ferric iron going before magnetite becomes stable, for example, at very low temperature, below 450 degrees?
Saying that all of the iron 3+ is going into epidote and hematite. So hematite becomes stable at these lower temperature conditions alongside epidote, and you can put quite a lot of iron 3+ in, and that's why the magnetite curve swoops around here.
Now, an important question. Do you think there is room for development of new or improved mineral normalization schemes for inferring ferric iron content in minerals? For example, from electron microprobe data. Or do you think that we have reached a point where this will not improve?
I think there's room for improvement and room to make estimates. I mean, I'm not a hardcore mineralogist, but you still, you know, we know things like titanium is often incorporated in biotite by deprotonation substitution, and yet we still normalize most people based on a 22 oxygen formula unit when you should be incorporating the effect of that. And so perhaps we won't get that much further with it, but I think there's room for educating all of us as, you know, when you're pulling out a probe analysis, you need to think about these things and deprotonation. So maybe there's more room there, that we shouldn't all just be pulling our analyses out and normalizing based on a standard number of oxygens or whatever.
That's a really good answer, Jacob. Thank you. Coming back to the importance of the different chemical systems, can you speak of to the relative importance of including manganese in your system components when investigating garnet-bearing metabasalt?
Yeah, that's a good question. And it's something I personally haven't done a lot of work on, but I have a fellow PhD here in Calgary who's done some work on that. The issue at the minute is that for dataset 6, there is no manganese-bearing amphibole clinopyroxene model. And therefore, all you'd be including would be garnet and ilmenite, I think, as manganese-bearing models. There may be a bit more scope for that in dataset 6, dataset 55, but I think, again, you'd be limited to the same 2 minerals. I've never really experimented with it. My intuition would be that I used to always think, because I worked in P-lights, that manganese was the most important thing for garnet stability. And it is important in metabasalts, but I think there are other factors, such as the calcium content, and Dave Patterson can comment here, I see he's there in the background, that may affect whether or not you should or will predict garnet in your rock. If I'm thinking of the classic ACF diagrams in Frank's book, and that garnet sits towards the low calcium, it's on the AFM join of an ACF diagram, and so you could see more garnet typically in low calcium metabasalts. But if anyone else has any comment, Dave.
I just might chip in there, just echoing what Jacob was saying. There's this student who recently completed here, Manuele Lazzarotto, and he looked at a prograde sequence going through the Flin Flon greenstone belt in parallel with a series of metasedimentary mineral assemblage changes. And what he found with the garnet stability in the metabazites was just what Jacob was saying. If you're modeling them, if you incorporate manganese, then the garnet takes on an unusually large stability field, and it's predicted to occur at quite low grade, which is not what's observed in the natural rocks. If you take the other extreme and you omit manganese, then the other problem is, well, then the garnet stability shrinks to the point where it never appears anywhere in the sequence, even though there is a garnet in isogret. So there seemed to be no really ideal way of dealing with this. And so I think that that's probably something that has got to be left for future developments.
Thank you, Dave. We have a comment in the chat from Daryl Henry, and he is saying that sometimes the simpler is better. And if, for example, you have graphite, assuming 12% iron 3+ is probably a good starting point for biotite. Would you agree with that, Jacob?
Yeah, no, I mean, all of my work looking at this is based on the work in West Central Maine. So yeah, 10, 11, 12% of iron 3+, that's fine by me. All right.
Excellent.
Okay.
I have one more question for you. I have one more question. So the more elements you add in your model, the more you have to pay attention to the degree to which the new introduced minerals will need to equilibrate with the rest of the rock. And yesterday, we discussed quite a lot plagioclase, for example. So would that impact, for example, how much you need to pay attention to the reactive bulk composition? The number of components that you consider?
Yeah, I think so. It's adding more complexity to what you've got to consider. There are more components that you have to track in terms of, are they in equilibrium with each other? And I think it's just making it harder for yourself, I suppose, when you're doing those effective. But maybe it's better in a way, because there's more elements to check, and so there's more checks on which minerals were close or getting towards equilibrium.